Okay, so we're continuing on with a scenario from the previous video. We launched a projectile from the edge of a cliff. The cliff had a height of 40 feet. We launched the projectile at a 35-degree angle above horizontal with an initial speed of 92 feet per second. And you can see over to the right, these are the position and velocity vectors that we obtained for this situation. So let's ask a couple more questions. Let's see, these, we'll just start this as question one again. It's not the same question one as on the previous video, of course. So our first question for this video will be, what were the speeds of the projectile let's say A, when it was launched, and B, when it hits the ground. When it hit the ground, past tense. Okay, so speed, remember, is the magnitude of velocity. So speed is the magnitude of velocity. So when we ask for the speed when it was launched, what we're looking for is the magnitude of the velocity at time 0. We also denote that by little v with no arrow and sub-0. And that actually was given to us. That was our 92 feet per second. So we don't really have to do any work for that one. Now, the speed when it hits the ground is going to be the velocity when it hits the ground. So when it hit the ground, we already figured that out. That was at time 3.95 seconds. So what we have to do for our answer to part B here is we've got to find the magnitude of the velocity at 3.95 seconds. Okay, so we have our velocity up above here. So we can simply put the 3.95 seconds in. So then we have the magnitude of the vector, 75, and negative 73.4. Now, if we were to draw a picture of that vector, okay, that vector, we go 75 units to the right, and we go 73.4 units down. Okay, and this right here would be the vector itself. And the next question we're going to ask is what the angle below the horizontal is for that vector. And you can see that because both sides of that right triangle, both legs are almost the same, that angle is going to be pretty close to 45 degrees. But for right now, we're just trying to find the magnitude of the velocity. And so let's finish that up. So we've got 75 squared plus negative 73.4 squared, square rooted. Okay? And it turns out that that is equal to 105 feet per second. So you can see that the projectile is going faster when it hits the ground than it was when it was launched, which may seem a little counterintuitive, but it's got a little assistance from gravity due to the fact that it's landing at a lower elevation than where it started. It turns out for this kind of problem that if the starting elevation and landing elevation are the same, then the velocity will be the same when it starts as it is when it lands. All right, so our second question is what angle to the ground or below horizontal, or let's just say what angle to the ground does the projectile hit at? That's pretty poor grammar, but that's the best I can do on the spot right here. So if I go back up here to this picture, what we've really got is the ground is along here, and the projectile is coming in like this and hitting right there. And so it has this velocity vector right here when it hits the ground. Okay? And what we're looking for is that angle theta, because that angle theta is the same as this theta up here above the ground, the angle at which it hits the ground. So if we can figure out that theta, then we'll have our angle. And you can see that that theta, the 73.4 is an opposite side from that angle, and the 75 is adjacent. So what we have is that the tangent of theta is equal to 73.4 over 75. And so from that, what we have is that theta is the inverse tangent of 73.4 over 75. Okay, and that turns out to be 44.4 degrees, which is pretty close to the 45 degrees that we predicted. Okay, so those are a couple things we can figure out. And let's ask one final question here. The final question is, let me get the blue pen back out. So question 3 is, what distance does the projectile travel through the air? Okay, so the question we're really asking is this. Here's our picture. Let me draw in red. The projectile goes like this. And I actually want to know what is the length of that red curve. That's what we're after. Okay, so remember, distance is rate times time. So let me put that in here. Let's do that in green. Distance is rate times time. Okay, now we know the time because we know that this thing landed at time of 3.95 seconds. It started at time 0, so the time elapsed is going to be 3.995. Now the rate is the speed, which is also the magnitude of the velocity. And the velocity is variable. So because the velocity is variable, the speed is variable, so to compute our product of rate times time, we're going to need to do an integral. All right, so let's go ahead and find the speed. So it's the magnitude of our velocity vector, which was 75, and then negative 32t plus 53. Okay, so we need the magnitude of that vector, which means we square each component. We add the results together and we square root. So that's the speed. And remember from a few weeks ago, distance is the integral of the speed over the time period we're talking about. So the time period is from 0 to 3.95 seconds. There's our speed, 75 squared plus negative, that's not a negative 2, okay, negative 32t plus 53 squared. And then times time, and the time shows up as the dt in here. Okay, so let me just point out to you, this is the rate, and this is the time. And what we're really doing is multiplying a rate times a time over a very, very small time interval, and then by integrating, we're adding up all those little distances to get the total distance. Now this this integral is kind of a pain to do by hand, so I went ahead and did it using some software, and we end up getting 330 feet. That's the distance the projectile traveled through the air. Now remember, so that would be where on our picture? That would be 330 feet. And you may or may not recall that the horizontal distance traveled was 296 feet. So we can see that distance traveled through the air looks reasonable. It should be more than 296, and in fact it is. So that wraps up this video, and that pretty much concludes the various things we would do. Well, actually, we have one more thing we'll do later, but let's put that on another video.